Problem 1353, maximum number of events that can be attended. So to solve this problem, we need to know one concept, and that's greedy. In other words, we need to know how to think optimally. And that just comes with intuition from a lot of practice. So this is a good place to start. So how do we solve this problem? Well, let's see how we solve the given example. Basically, we're given an events array, and in the events array, we have a bunch of events, and each of these events happens within a specific time window. So event 1 happens between times 1 and 2, event 2 happens between times 2 and 3, and event 3 happens between times 3 and 4. So the goal is we want to attend as many events as possible, given it takes one full day to attend an event. So the way we solve it is event 1 we attend at time 1, event 2 we attend at time 2, event 3 we attend at time 3. But how do we generalize this idea? Well, first of all, given a greedy problem and knowing how to think, we have to utilize given information. There's some pattern, some way of thinking about the information given to us that's going to help us. And every event we notice is defined by a start time and an end time. So perhaps knowing which event to choose have to do with how these start times and end times are defined. Well, and then let's think about it from a chronological perspective, right? Well, logically, we have a bunch of events and we want to fill it from times 1, 2, 3, etc. to infinity, basically. And the goal is to basically, we want to put as many events associated with each time as possible. So basically, we want to work our way forwards, right? We want to start by putting events in earlier time slots before going on to the later ones, right? That's just a natural intuition that we should have. So how do we go about this? Well, since we care about ordering the events from a chronological perspective, right, from time 1 onwards, then perhaps the start times have the most importance. So consider the cases of the start times for event 1 and event 2. What if their start times were equal? Well, then in that case, we have the following example. Let's say event 1 takes this much time and event 2 happens within this duration. Which event do we choose first given just these two events and nothing else? Well, let's say we chose event 1. What if we attended event 1 right here? Well, then we can only attend event 1 because event 2 has already passed, right? We have to attend it somewhere here to go to event 2. So what this basically tells us is if we were to choose event 1, like let's say here, it leaves the possibility of potentially not being able to attend an event that has a shorter time frame. So let's suppose that this is 0 and this is 2. This is 0 and this is 1. Well, and let's say we just so happen to attend event 1 at time is equal to 1. Then obviously there's no way we can attend event 2 because it has already passed. So what this should allow you to deduce is that we should choose the event that has the shortest window of happening before choosing other events with longer windows because naturally, if the event has a much stricter time frame, then that's more restrictive, and the less restrictive cases, which are indicated with longer time frames, should be saved last so that we accommodate all the restrictive cases first before accommodating the least restrictive ones. So in this case, the optimal way is to attend event 2 first, such as any time within here, because no matter where we attend event 2, we will always have this much time left guaranteed for event 1. So that's the idea. Given two events, right, so let's write this down, given two events with the same start time, then what we should do is we should choose the event with the earliest end time, because this basically corresponds to the event with the smallest time window. And that's the core understanding that makes this a greedy problem, right? This is the greedy part. We always choose the event with the earliest start time given two start times that are the same. But obviously the start times don't have to be the same, like in the example where event 1, for example, happens between 1 and 2, and event 2 happens between 2 and 3. If we draw it out, it looks something like this. Well, if they are not equal, then naturally we should choose the one that happens earlier, because for the same idea, if we were to attend the one that happened later first, such as event 2 right here, then obviously there's no way to attend event 1. So, just from basic intuition, we should be able to see it is always optimal to attend events with the earlier start time given their start times are not the same. And that's the basic logics we need to deduce, and from there we can program this up in Python. So we're going to sort we're going to sort the events because, again, we're going to attend the event chronologically, starting from time 1 and onwards. So basically, whichever event that we attend has to be where the event start time is the earliest, right? That's what we have deduced. And so that's kind of a priority. So how do we store priority? Well, we do that in priority queues, and we import the library here, and we declare a heap, but by using an array, because heaps, min heaps are stored in arrays in Python. So with that, well, what can we do? Well, we're going to basically associate an event at every time. And how many units of time are there? Well, for t in range of 1 to, well, what's the maximum time? It's not infinity, it's the end time of, the latest end time of the events in events. So what is that element? Well, n time, right, the grand n time is going to be the max of event of 1 for event in events. So event 1 takes the second element of the list in the list of lists that represents events, which denote the n time of the event. So this is what it's telling us, the maximum n time in the list of events. And with that, that's going to be the n time, and plus 1 because this has to be inclusive of n time. So what do we do? Well, the first step, as we said, is we're going to need to put all the events with the time that is the earliest time, and that earliest time is at most t. So what we have to do is we have to iterate through every single event and events and see which one has that associated event. But that takes a while if it's not sorted. If we sort it based on the first element, meaning of the internal lists, which represent the start times, then that'll be a lot easier. So events.sort. So with that, we can do another counter, let's call that j. And j is going to basically allow us to iterate through every event and events. We're going to say while j is less than the length of events, and the current event, which is at events j0, is less than or equal to I. Basically, all events that happen at most prior to the earliest time t, the current time t, we're going to add that to the heap. And we do heap q dot heap push. And what do we push it to? We push it into the heap, and we push the events j of 1. And I'll explain that in a bit. And after that, we just increment the counter. So j plus equal to 1. The reason why we add j of 1, well, j of 0 gives us all the start times, right? And j of 1 gives us all the end times. Like we said, if two events have the same start time, then we choose the event with the earliest end time. So we have to push in the end time because we have to do processing of the end time after we push in the property of the start time, which we have to push the ones that start the earliest, and the earliest have to be at most t. And that's the whole idea here. And j, we just iterate through every event and events. So now we process the end time while the heap is not empty and the events, or not the events, the heap of 0 is less than I, or less than t. Then we do heap q dot heap pop of the heap. And so what this is doing is that, well, what is stored in the heap? The heap, we store all the end times. And the end times are sorted based on ascending order. So whichever event had the earliest end time is going to be at the top. At the very top of the heap, well, that's the element at index 0, hence this. And what I mean when I say it's less than t, it means that the event is basically happening before it started, right? Like it can't end before it started, meaning we can't have an event that ended before the time that we're currently trying to assign, which is t. So that basically sorts that out. It makes sure that we're only considering events that happen at time t, or at the latest t, and happen at the end at a later date, right? It cannot end prior. So that makes sure we're considering the right events. And from there, we know that the heap basically stored all of the end times from least to greatest. So that means the current minimum value at heap 0 is going to be the event that we have to attend. So how do we represent that? Well, if we are attending the event, we no longer need to consider that event for future processing. So if the heap is not empty, then we just do heap q dot heap pop, right? We have attended the event and we no longer need to consider it, and therefore we added the increment of 1 to answer to denote that. And that's the whole logic. We just return the answer and we're done. So let's run it to make sure it works. And that is not the case because we did not define answer. And that should work. Here we go, so let's run. Or submit, rather. And there we go, that's the solution.